Last lesson, we defined the Laplace transform and built three fundamental pairs. U of t goes to 1 over s, delta of t goes to 1, and e to the minus at goes to 1 over s plus a. Today, we add the manipulation tools: shifting in time, shifting in frequency, differentiation, and integration. With these in hand, any signal you can build from the table can be transformed by inspection. First, the time shift theorem. Suppose we have a signal f of t with transform f of s, and we delay it by a second. F of t minus a multiplied by u of t minus a, so it stays causal. Set up the Laplace integral. The unit step kills everything below t equals a, so the lower limit becomes a. Substitute tau equals t minus a, and the integral splits into e to the minus as times the ordinary Laplace integral of f. The conclusion? A delay of a second in time becomes multiplication by e to the minus as in the s domain. The magnitude is unchanged, only the phase shifts. Now the frequency shift theorem, also called S-shift. If we multiply f of t by e to the minus at in the time domain, what happens in the s domain? Plug it into the integral and combine the two exponentials. E to the minus at times e to the minus st equals e to the minus s plus a times t. So the integral has the same shape as the original transform, with s replaced by s plus a. The result? Multiplying by an exponential in time shifts the s variable by a. This is the symmetric mirror of the time shift theorem. Differentiation in time. This is the property that turns differential equations into algebra. Take the Laplace integral of f prime of t and apply integration by parts. U equals e to the minus st, dv equals f prime of t dt. Then du equals minus s e to the minus st dt, and v equals f of t. The boundary term evaluates to minus f of 0 plus 0 at infinity, because res greater than the abscissa of convergence. The remaining integral is just s times f of s. Putting it together, the Laplace transform of f prime equals s f of s minus f of 0. For the second derivative, apply the rule twice: s squared f of s minus s f of 0 minus f prime of 0. Each derivative becomes a power of s plus the initial conditions. Integration in time. If we integrate f from 0 to t, what happens in the s domain? The mirror of differentiation. Instead of multiplying by s, we divide by s. The Laplace transform of the integral of f from 0 to t equals f of s over s. The proof swaps the order of integration in the two-variable integral and splits naturally. The takeaway is symmetric. Derivatives correspond to multiplying by s. Integrals correspond to dividing by s. This is exactly why circuits with capacitors and inductors collapse into algebraic networks in the s domain. One more useful property. Multiplying f of t by t in the time domain corresponds to taking minus the derivative of f with respect to s in the s domain. As a quick application, t times u of t goes to minus the derivative of 1 over s, which is 1 over s squared. We just derived another transform pair without doing any integral. Here is a running properties table for quick reference. Time shift adds e to the minus as. Frequency shift replaces s with s plus a. The first derivative becomes s f of s minus f of 0. The second derivative adds an s f of 0 and an f prime of 0 correction. Integration divides by s. Multiplication by t differentiates with respect to s. Time scaling, f of at maps to 1 over a, f of s over a. These 8 rules, plus the 6 pairs from last lesson, cover essentially every signal in linear circuit analysis. Time for a small but complete example showing why this matters. Solve y prime of t plus 2y of t equals 0, with y of 0 equals 1. Take the Laplace transform of both sides. The differentiation rule gives sy of s minus 1 for the y prime term plus 2y of s. Group s plus 2 times y of s equals 1. Algebra. Y of s equals 1 over s plus 2. Recognize this as the exponential pair from last lesson, so y of t equals e to the minus 2t. We just solved the differential equation by doing pure algebra in the S domain. Next lesson, we will handle more complex right-hand sides using partial fractions. 3 takeaways. Time shift maps to e to the minus as, and frequency shift replaces s with s plus a, the symmetric pair. Differentiation in time multiplies by s and pulls in initial conditions. Integration in time divides by s. With these manipulation rules plus the 6 basic pairs, you can transform almost any signal in your head. Next lesson we go in the other direction, inverse Laplace and partial fractions.